Hello, so let me know if you guys have any questions or anything. Hey Alexis, how's it going? I don't know if you're able to check out some of the Canvas stuff yet, Alexis. Yeah, so let me know if you guys have any questions or anything like that. For some reason, it seemed like some of my students were in a different remind group than the general chemistry one, so you guys might not have been getting some of my announcements from previously. So I apologize if there's any confusion because of that. But yeah, if you guys want to go over any homework problems or anything like that, we can definitely do that too. Okay, cool. Yeah, I don't know if you saw from before, but yeah, I've been trying to post some stuff on Canvas since we have been out of school. So I know it's probably a lot at once, so just take your time and stuff. Um, I'll be pretty lenient with due dates, especially because I know some of you guys might have just gotten to Canvas recently all of a sudden. So yeah, don't worry about it. Just let me know if you need any help or anything. We do have a quiz tomorrow, but even with the quizzes, you can if you can't tomorrow, you can take it next week. So it's pretty lenient as far as things are going right now on Canvas. And next week will be pretty simple. We're just gonna have a study guide that I'll give you guys on Monday, and I'll give you guys pretty much the whole week just to work on that. Just to let me know if you have any questions or anything. And then we'll have our test next Friday, April 3rd. And then after that, we have like a week off for spring break. So if you guys need to, you can use some of that time to catch up if you still have to catch up on some assignments. Yeah, let me know if you guys have any questions or anything, or if you want to go through any problems or anything like that, or if you just have any concerns at all. I guess I'll just start off with tomorrow's quiz. It's going to be on these gas laws here. All right, so we have Charles' law, which is about volume and temperature of a gas being directly proportional to each other. So if you increase the temperature of a gas, the volume is going to go up for the gas as well. So they follow the same pattern. If you decrease the temperature of a gas, the volume is going to go down. Right, so that's one of them, Charles' law. All right. We also have Guy-Lussac's law, which I'll put over here. All right, so Guy-Lussac's law is also directly proportional. So that's with pressure and temperature. So if you increase the temperature of a gas, it's going to have a higher pressure. It's going to expand, and so it's going to have more collisions on its container and on the surfaces of what it's colliding with. If you decrease the temperature, the pressure is going to go down, right? So it's kind of like, excuse me. Good examples could be thinking of like tires from cars or on bikes. If it's a colder day, usually your tire pressure on your car is a lot lower, right? Because if the temperature is going down, they're not moving as fast, not spreading out as much. So they're not going to be making very many collisions on the surfaces around them or on each other, right? So if temperature goes down, pressure goes down. If temperature goes up, pressure goes up. So this one's directly proportional. Charles' law, they copy each other. If temperature goes up, so does pressure. If temperature goes down, so does pressure. And Guy-Lussac's law is also directly proportional. So if temperature goes up, so does pressure. If temperature goes down, so does pressure. So they follow the same pattern. Apart from those two, we also have Boyle's law. Right, so that's Boyle's law over here, and that's with pressure and volume. And so this one's different than these two, because with these two, they're directly proportional. And for this one, they're inversely proportional. So if you increase the pressure on a gas, the pressure goes up. The volume is going to do the opposite. It's going to go down, right? So they do the opposite trend of one another. It's kind of like if you have a balloon, for example, and you put it under a lot of pressure. Maybe you submerge the balloon at the bottom of a pool, or you just sit on it, for example, without it popping. The pressure on that balloon's gas is increasing, so the volume should go down. It should contract more. Hey, Santino, how's it going? Right, and again, all these notes are on Canvas as well too. So in case you're just kind of getting started with Canvas, all these notes are on Canvas as well. This is the ideal gas law. So you have pressure, volume, moles is N, T is temperature, and R is a constant. It's the gas constant, which it depends on what pressure you're using or what pressure you're looking for. There's gonna be two different R values you can use. So for tomorrow's quiz, it's really just gonna be it's just gonna be 4 problems, and it's just one of each of these. So each problem is going to be about one of these gas laws. So it's going to be a pretty quick quiz. It won't be too long or anything. But just let me know if you guys have any questions, if you want to look at any examples at all. We'll just have that quiz tomorrow. And like I said, next week on Monday, I'll give you guys a short little study guide. And you'll have a whole week to work on it. I don't know if it's necessarily short. I guess maybe it's like a medium size. It's like 3 pages. But I feel like we've had longer study guides in the past, so it's definitely shorter than what we've had during class. But yeah, so it's probably like a medium size, about 3 pages. But we'll have the whole week to work on it, and we'll have our test on that Friday. Yeah, so I'm just inputting points right now into Q. I haven't actually made anything like graded yet to count, just because I know there's some technical issues with that, with just circumstances with other students who maybe don't have internet access, who don't have a computer, things like that. 'Cause if I make it graded, then it's gonna basically drop their grade, which is, I guess you can say, there's like a fairness issue with that, because they just might not have internet access or the means to look at these assignments right now. So right now, if you see that you have the points in these assignments, you're good. Don't worry about it. Your grade's pretty much going to be frozen as the same way it was before we left school. So your grade should pretty much be the exact same the way it was when we last saw each other. But if you see that you have the points in those assignments, you're good. So it will eventually count. I'm not making them count yet, just for those students who don't have internet. Celsius Fahrenheit equivalent. Oh, so with Celsius, 0 Kelvin is 270. Sorry, yeah, 0 Kelvin is negative 273 degrees Celsius. Right. So yeah, just kind of like if you're trying to convert from Kelvin to Celsius, which we don't usually do because we want Kelvin and we try to go from Celsius to Kelvin, but absolute 0 Kelvin is negative 273 degrees Celsius. For Fahrenheit, you don't have to worry about that. Off the top of my head, I don't even remember what it actually is. Here, let me see if I can find it for you guys, though. Yeah, you don't have to worry about Fahrenheit, though. Fahrenheit, absolute 0. Yeah, we're not going to use Fahrenheit, but for Fahrenheit, yeah, it's like negative 459.7 degrees Fahrenheit, but we're not going to use Fahrenheit, so I wouldn't worry about it. But yeah, for absolute 0, it's 0 Kelvin, but then it's negative 273 Celsius. What's Boyle's law again? Boyle's law is this one up here. So the initial pressure of a gas times the initial volume of gas equals the later pressure times the later volume, right? So again, this is inversely proportional for Boyle's law. So if you decrease the pressure, the volume is going to expand, right? So it's kind of like if you're at the bottom of the ocean, let's say like 20 feet below the surface of the ocean, you have a lot of pressure on your gas. So this pressure is really high on the gas inside your body, like your lungs, your blood. Excuse me. So the volume is small. But if you suddenly submerge and just push yourself to the surface too quickly, the pressure is suddenly dropping, which means the volume is going to do the opposite. It's going to expand. And that's when you can have the bends, which is a pretty life-threatening thing. Excuse me. Sure, we can do that. I don't think the combined gas law is going to be on the quiz tomorrow, but it's definitely one we can look at. So, sometimes when we see the combined gas law, we actually do see moles changing, but you're not going to have to worry about that. The one that we're looking at today, not today, but the one that we're looking at in this unit is basically assuming that the moles is constant. So it really stems from the ideal gas law, right? So I'll just show you. You don't have to worry about this too much. But I'll just show you like a derivation. So for the ideal gas law, we have this thing. If you're trying to solve for R, the constant R, you divide NT on both sides, right? And R is a constant, right? So it's always the same number. It's not changing. It's not a variable. So if you get R by itself, it's PV over NT. For the combined gas law, we're looking at like a before and after situation, kind of like with these other ones, Charles law, Guy-Lussac's, Boyle's. We're looking at a before and after situation, but we're assuming the moles is constant. So basically, if I have some initial pressure, initial volume, initial temperature, and moles, and then some later pressure, later volume, later temperature, and moles. Again, I got these just from R, using the ideal gas law solving for R. You're not gonna have to like derive this or anything like that. It's just gonna be like a problem you have to plug and chug pretty much. But R is a constant, so it equals this ratio. But with the combined gas law that we're looking at in this unit, we're assuming the moles is constant. So that's why there's ones down here, but twos over here. The ends, however, are constant. The moles are constant, so you can just cancel them out on either side. So that's the combined gas law. Now, if you want to look at an example, it just has multiple things changing at once. So sometimes you just have to be careful with the wording on these examples and these problems because, for example, if the problem just has volume and pressure, it's going to be Boyle's law. If it just has temperature and pressure, it's going to be Guy-Lussac. If it just has volume and temperature, it's going to be Charles. You might sometimes see a little curveball, like you might see pressure and volume, and then a temperature, right? But it might say something like this temperature, I don't know, 300 degrees Celsius is constant. That means it's not changing. So it's kind of like just extra information you're not going to use. But since pressure and volume are in there, it's going to be Boyle's law. So it's important to kind of be careful. So with combined gas law, let me see if I can find an example for you guys. I don't want to just take numbers out at the top of my head. I mean, I could, but let's try to get something a little bit more reasonable. Combined gas law example. By the way, this website, if you guys are interested, I'll post it in the comment section here. They have lots of good examples of different chemistry topics, chemteam.info. It's not just like combined gas law. They have a page for any sort of topic, stoichiometry, anything really. And they're really good worked out examples. Sometimes I get some my examples from here too. Let me see if I can find an example of combined gas law. Okay. Okay, so this one says, I'm just gonna write it out. You have 2 liters. Here, let me make some room. Sorry, thanks for your patience, guys. 2 liters of a gas at 25 degrees Celsius and 745 millimeters of mercury. What's the volume? So we know we're going to look for V2, the later volume. What's the volume at STP? All right, so keep in mind STP. Oh, that's a good reminder there. STP is standard temperature and pressure. All right, so that's from the notes, but in case you forget, standard temperature and pressure, I'll just include it in parentheses here on the side. That's 273 Kelvin, or 0 degrees Celsius. And the pressure is 1 atmosphere. We're looking at millimeters of mercury, though, so that's 760. Right, so let me just double check everything. Looks good. Yeah, cool. All right. So yeah, it's cooling down. So this part in parentheses wasn't included in the question. I just placed it here just in case you guys forgot. But this is a good example for combined gas law. We have 2 liters of a gas, that's volume, at 25 degrees Celsius, that's the temperature, and then 745 millimeters of mercury, that's a pressure, right? So we have an initial volume V1, an initial temperature T1, an initial pressure P1, and we're trying to find V2. We're trying to find the volume. Just a quick question, guys. When you're looking at me do these examples, do you see it like a mirror? Is it all backwards, or do you see it like the way it's supposed to be written? I just want to make sure I'm not showing you guys everything backwards, because like I don't know if you guys know what I'm talking about. Like, hopefully it doesn't all look like it's written backwards, because when I'm looking at it right now, it looks like it's backwards. It shouldn't be that way for you guys, so I don't know. Yeah, hopefully it's not backwards. Just let me know. Like, it's fine right now. Okay, cool. Yeah, because when I'm looking at it right now on the screen, it looks like I'm just looking in the mirror. I'm looking at backwards sentences right now. But anyways, so the combined gas law we have here, thank you, by the way, Ryan. It's P1 V1 over T1 equals P2 V2 over T2, right? So we have this combined gas law right here. And so standard temperature and pressure, again, is 0 degrees Celsius, 760 millimeters of mercury. Again, this is from the notes. The standard pressure could also be 1 atmosphere, or 101.325 kilopascals. Basically, those conversion factors we looked at a little while ago. And so I'm looking for V2. I want to get V2 by itself, right? So we just got to algebraically get it by itself. So one thing we could do is multiply both sides by T2, right? So multiply both sides by T2. And then we could also divide both sides by P2, right? So I'm going to multiply both sides by T2 so it cancels out. I'm going to divide both sides by V2. So I'm just going to multiply both sides by that ratio, T2 over V2. So let me see if I can show you guys. T2 over V2. That way it cancels over there. And then we end up with, I'm looking for the volume. Sorry, guys, I should be moving pressure. My bad. I'm looking for the volume. Sorry about that, guys. That should be P2, not V2. My bad. Sorry about that. We're looking for the volume, so I should be dividing both sides by P2, right? Sorry about that. So then we're going to get that V2 is T2 times P1 times V1 over P2 times T1. All right, so we have this whole thing right here. Sorry for that mistake earlier. It should have been P2, not V2. I'm looking for the volume. So I want to get V2 by itself, so I multiply both sides by T2 so it cancels, right? So it's going to be up there in the numerator. I divide both sides by P2 so it cancels, so it's going to be down here in the denominator. So that's how I get all that down there, right? P2's on the bottom now, T2's on the top. Now we just have to plug in our values, right? So I'll move it up here for the sake of room. So V2 is going to be T2 times P1 times V1 over P2 times T1. Now, the second temperature here is 0 degrees Celsius, right? So I know for T2, it's standard temperature. That's 0 degrees Celsius, but I need this in Kelvin. So just add 273. So it's 273 Kelvin. All right, so 273 Kelvin. P1 is my first pressure, 745. Kind of running out of space. I'm going to leave off some of these units. And my first volume was 2 liters. Excuse me. So, and I'm divided by P2 times T1. Right, so far I have my numerator here. I have to do the denominator still. But again, T2 was standard temperature, which is 0 degrees Celsius, but you need it in Kelvin, so that's 273 Kelvin, because again, so always add 273 if you're trying to get to Kelvin from Celsius. P1 is my initial pressure, 745 millimeters of mercury. I just left off the unit because it's running out of space here. And my first volume, my initial volume is 2 liters. That's why there's a 2 here. I'm going to divide it by P2 times T1. So P2 is 760 millimeters of mercury. So 760 is going to be down here. And then T1 is my initial temperature, which is 25 degrees Celsius, but I have to add 273 to that, right? So 273 plus 25, you're going to get 298, right? So 298 Kelvin. And so, yeah, we just have to plug all these things in. So I left my actual calculator over there. I'm just using my phone for right now. So 273 times 745 times 2 and divided by, let's make sure I have parentheses here, divided by 760 times 298, 298 times 760, okay. Yeah, so the volume is just going to be 1.80, about 1.80 liters. Let me double check because I don't always trust my phone calculator. But let me see if yeah, 1.80 liters, cool. Yeah, so that's the final answer for your combined gas law example. So again, let me know if any part of this is confusing, if there's a specific step, like maybe the algebra at the beginning, or maybe why the temperatures suddenly look different. Again, we just have to add 273 to make it Kelvin. You can never put a Celsius temperature in here. It has to be Kelvin. So just make sure you add 273 to it first, like no matter what. And the next unit's going to be the opposite. The next unit, we have to use Celsius, but we'll get there later. Yeah, so let me know if you have any other questions or if you saw. And other than that, there's no other assignments tomorrow. It's just like 4 questions. It's pretty quick. And yeah, we'll have our study guide on Monday. And we'll just be working on that pretty much all week until the test on Friday. And then we'll be done with this unit. And then it'll be spring break. And then after spring break, we'll start the next unit. Yeah, that website's pretty good if you want to check it out in the comment section. There's good examples of like pretty much every topic you can think of in chemistry. Here, I'll put a link down of like the main page. That's the main like home page right there. It has pretty much every single. Yeah, so let me know if you guys have any questions. Yeah, Hg is mercury, so that's why we call this millimeters of mercury for the unit. Just based on looking at the pressure values from like a thermometer, pretty much. So yeah, millimeters of mercury. It's the same thing as torr, right? So it could have said 745 torr, and this would have just been 760 torr. Like it's the exact same unit. Well, it's talking about the pressure of the gas within the actual like thermometer, like above the liquid of mercury. So yeah, it's kind of weird because mercury, it's a liquid, but they're talking about the pressure of the gas within the container, within the between the sealed part on the top and the liquid, the surface of the mercury. So yeah, let me know if you guys have any other questions or anything. If you want to look at any examples. I'm sure it is, but when it comes to these different phases of matter, it has to be very specific temperature and pressure values. So it's a little more difficult than just cooling it down because you have a liquid mercury, you'd think just maybe cooling it down, you'd get a solid, but it's probably more difficult than that. Let me see. Pressure and temperature for solid mercury. And the same thing for other things like solid oxygen, stuff like that. It might be kind of impossible to do things like this on Earth. We might not see something like these things solid on Earth. So yeah, normal room temperature mercury is always liquid, but on Earth, if it's at 1 atmosphere, which is standard pressure, so it's not too unfeasible, it's not too difficult. You just have to cool mercury down to like negative 38.8 degrees Celsius. So you just have to cool it down enough, and you can make it solid. I do not. I don't really play video games much, to be honest. I'm not that good. Um, I kind of stopped in high school around the time all my friends were playing Halo 2 and Halo 3 and stuff like that. And first person shooters became really popular. And I realized I was more of a Donkey Kong Country, Super Mario Brothers kind of guy. So I kind of just stopped at that point. Kirby's pretty fun too. Eating oxygen. Yeah, let me see. Yeah, very, very, very cold. It has to be super cold for oxygen. It can be at normal standard atmospheric pressure, like 1 atmosphere, but it has to go down to 54.4 Kelvin. 54.4 Kelvin, that's pretty cold, right? Because 0 Kelvin's like the coldest possible temperature. So it has to be extremely cold to get solid oxygen. That's cool. I wonder if there's actual photos. Yeah, I mean, you'd only see things like this in a lab, pretty much. So yeah, it's possible. It's just not something that would happen by itself naturally. It'd have to happen in a lab, pretty much. But no, yeah, I've been kind of flirting with the idea of maybe getting a Switch, but they're just so expensive. Oh, dry ice is CO2. Yeah, so CO2 would be dry ice. And that's it sublimates because at this atmospheric pressure, um, it basically goes straight to the gas phase. Here, I can show you guys. There's a graph that kind of points all this stuff out pretty well. Let me see if I can find it for you guys. All right, this might be the best. I don't know if how it's gonna show up in a comment. Yeah, I don't know if it's gonna show up in a comment. But here, I'm just gonna open the image in a new tab and I'll show you guys if you're interested. I don't know if that takes you to the right place or not. Oh, cool, it does. So yeah, it's an image in a new tab, and you'll notice on this graph, it has the different phases of matter in these different chunks, like solids on the left, gas is this big part that's on the bottom and goes over to the right, and liquids that little pocket over in the center top. So you can see if you're at a low enough temperature and you have enough pressure, you can just go straight from the solid phase to the gas phase. You can just skip right over. Right, so dry ice or carbon dioxide (CO2) at atmospheric pressure and at atmospheric temperature and pressure, if it's a solid, it goes straight to sublimation. It just becomes a gas. It doesn't go over to that liquid phase. Yeah, so dry ice would be a solid. Let me see. The solid hydrogen element. Yeah, so hydrogen is the lightest element, so it moves pretty fast, right? So it typically has a pretty high amount of kinetic energy. That's why it's pretty much always a gas. So with solid hydrogen, its melting point would be, yeah, like 14 Kelvin. Pretty cold. 14 Kelvin. So yeah, that's why hydrogen's pretty much always a gas. No, I never played that. I only played like the Super Nintendo original one, and then Double Dash on GameCube was pretty fun. Like Double Dash a lot. Yeah, Double Dash is probably the best one because you get to have someone helping you out with attacking while you drive. Yeah, let me know if you guys want to go through any other examples, or if you just have any questions at all. Yeah, tomorrow's quiz is just gonna be like 4 questions. It's pretty. I don't remember. It's been a while. It's been a few years. I just remember Rainbow Road being fun, but also really scary and nerve wracking because there was like no walls, and I feel like the road's extra slippery. So if you're going too fast, you don't brake enough on a curve, you just like go off into space. That was a fun one. And like Bowser's Castle, Waluigi's Mansion or Stadium or whatever it is. I don't remember exactly. Yeah, Double Dash was fun. I like that one a lot. I was never too into the Crash Bandicoot ones. Those ones are okay, but like the Crash like go-kart games, like I feel like it's more awkward to turn and brake. It doesn't feel as smooth as Super Mario Kart. Yeah, let me know if you guys have any other questions or if you want to go through any examples or anything. But yeah, like I was saying, just as long as you're staying on top of the work as best as possible, you're totally fine. I'm gonna be pretty lenient with the due dates, especially since some of you guys maybe just started reaching out into Canvas or just started looking at it. Um, what was I gonna say? But yeah, I'm just gonna input the points onto Q, and then eventually, once we figure out what's gonna happen, once we come back like May 5th, then we'll see. I'll make them all graded so they'll actually go towards your grade. No, actually, Lucas, it's just 4 questions, and one question's gonna be Charles' law, one's Guy Lussac's law, one's Boyle's law, and then one's the ideal gas law, and that's it. There's like no definitions or anything. There'll be some questions kind of like that on the test next week, but yeah, we'll see more of that later. Although I don't know if you saw the quiz from Monday, Lucas, but on Monday's quiz, there was like a couple of more conceptual questions like that. There was a question talking about the definition for pressure and definition for temperature. Oh yeah, sure. Let's check that out. Gas stoichiometry. Um, See if I can find a good example. So they're pretty much just like typical stoichiometry problems, but there are some that are quicker, where you just look at the coefficients as just the values of the what's it called, the liters themselves. Let me see. Yeah, let's do one of those. So look at the decomposition of hydrogen peroxide. So let's say, hmm. So I'll show you a quick one first. All right, so this is the decomposition of hydrogen peroxide. So I'll just balance it real quick. All right, so this is a quick one. This is like the quickest possible example you can probably see. There was one like this in the notes. It was the first example. And so in this case, we have zero point 0.5 liters of water being produced from the decomposition of hydrogen peroxide. So how many liters of oxygen would be produced? And so, yeah, this should be a gas. These should both be gases over here. I'll just put the G down below. Should be both be gases, although this one's a liquid. All right, so this is the phases of matter. The H2O2 is a liquid, but it creates these two gases as it decomposes. So your given here is 0.5 liters of H2O. Right, so just don't have a lot of space on this board, unfortunately. So liters room, your given is H2O. You're trying to find liters of oxygen. Right, so your given is liters of H2O, and you're trying to get liters of oxygen. Now, instead of using 22.4 in the moles here, because you're just going from liters to liters, you can actually just use the coefficients in this equation. So this is a really quick example. So let me show you what I mean. So I'm not really going to draw the path. I mean, I did draw the path, but I'm not really going to use it in this example. So I have 0.5 liters of H2O, and I'm trying to just get liters of oxygen, right? So I drew the path here, but I don't really need to use it in this question because I'm just going from liters to liters. The ones where you go from like maybe grams to liters or liters to grams, then it gets a little bit more complicated because you have to use the mole, the mole doorway there in the middle. I drew it here, but I don't really need to use it, truth be told. I'm just trying to go from liters of H2O to liters of oxygen. And so keep in mind, if you're just going from liters of one gas to liters of another gas, you can use those coefficients as your liter ratio instead of your mole ratio. So we've always used the coefficients in the past as our mole ratio. This time we can use it as just our liters ratio because I'm just trying to go from liters of one gas to liters of another gas. So the coefficient in front of H2O is a 2, so I'm going to put that down here. And the coefficient in front of oxygen is 1. So this is like the quickest example, pretty much. I'll show you guys a longer one after this. I'm just going to do 0.5 divided by 2. So I'm just going to get 1/4 of a liter of oxygen. Right? So if I get half a liter of H2O forming, I'll just get 1/4 of a liter of oxygen forming. So this is the quickest example I can really show you guys. I'll show you guys another example too, though, one that's probably a little bit longer. Let me see here in case you guys want to look at that one any longer. So again, my given was 0.5 liters of water. I'm trying to go from liters of water to liters of oxygen, right? But instead of using this whole pathway here, I'm not really even using this, truth be told, right now, because I'm just going from liters of one gas to liters of another gas. So all you need are these coefficients. Instead of using it as the mole ratio, it works the same way, but you're using it as the volume ratio, the liters ratio. So this 2 is because there's a 2 in front of H2O, and this 1 is because there's a 1 in front of O2. So it's going to be 0.5 divided by 2, so 0.25. Right, so that's the quickest example. I can show you guys a longer one. For one of these longer ones I'm going to show you guys, if anything, I would chunk it into parts so it's not like too crazy at once. But here, let me take some time to write it down for you guys real quick. So this is probably the hardest possible question that you'd see on the test. Yeah, exactly. If you're just going from liters to liters, liters of one given to liters of some other substance, exactly. It's really quick like that. You just use the coefficients as your volume ratio instead of your mole ratio. So you can skip that whole moles to moles part. And you don't have to use 22.4 either. I mean, because you could put it on there and do the whole path. But like, because if you did that whole path, like here, it would look like this, right? So I'll show you the long way and the reason why we can skip it. Right, so it was still 2 down there, and then 1 up here. So if I did the path on the example I just showed you guys, if I did the path, it would look like this, right? But if I did the path, 22.4, can't really see what I'm doing, is going to cancel there. And so really the only things at play are the numbers for the coefficients. So that's why it looks so short, right? So yeah, that's why you can skip the whole mole room and the 22.4 and stuff. It's just gonna not make a difference. But let me show you a longer type of problem. So let's say we have 4 grams of hydrogen peroxide, 4 grams of H2O is at All right, so it's the same reaction equation. It's hydrogen peroxide decomposing. Right. So same reaction equation here, but it's very different. So in this case, I have a few givens. I have grams of H2O2, and it's decomposing. I took out some of the words here just to save space. I just went straight to the other givens, but it's decomposing in a sealed container that's at this volume of 250 milliliters and this temperature of 200 Kelvin, right? So we're trying to figure out basically, I forgot I'm trying to figure out what the pressure is in atmospheres. It's hard for me to read backwards, sorry. So we're trying to figure out the pressure in atmospheres. This one's a lot longer. So let me show you how this one looked like. For something like this, notice my given was H2O2 in grams, and I'm trying to find the pressure of oxygen, right? So for something like this, we're going to end up using the ideal gas law at the end of it. So I would, if I had a problem like this on a test, I would chunk it into parts a lot more clearly. So part A would just be trying to figure out how many moles of oxygen we're using. And then basically part B would be the ideal gas law part. So we have the decomposition of hydrogen peroxide here giving us 2 moles of H2O and 1 mole of oxygen, right? So same reaction as before, but in this case, I have grams of H2O2, right? So I have grams of H2O2, and I'm trying to figure out the pressure of oxygen. So that means I need to use the ideal gas law. Right, so I need to use that ideal gas law, PV equals nRT, for oxygen. But if I'm looking for the pressure, I have volume, right? The volume's up there. It's 250 milliliters. I have temperature. It's 200 Kelvin. And I'm looking for pressure, but I don't have the moles of oxygen. I have grams of hydrogen peroxide, but I don't have moles of oxygen. So I'm going to go from grams of hydrogen peroxide to moles of oxygen here. Right, so I'm going to start in that room and ends right there. So this is my path. I'm starting with grams of hydrogen peroxide. I'm going to try to get to moles of oxygen. I know I'm not writing everything down the mole house like usual, but it's just there's not a lot of space here. So we're going to have 4 grams of H2O2. I'll work it out on the bottom here. And we're trying to go from grams of H2O2 to moles of oxygen. So I'm leaving off some of the stuff here for the sake of space. All right, so there's my little setup. So I'm going through 2 doorways, so I'm multiplying my given by 2 fractions. Right, so this is going to be the molar mass of H2O2 and then 1 for mole. So the molar mass of H2O2, that's 32 plus 2, so it's 34. Right, and then I have to use the coefficients for the mole ratio here. So I'm going to be going from moles of H2O2, which is 2, to moles of oxygen, which is 1. So it's going to be 1 on top and 2 on the bottom. All right, so again, this 1 is just from the coefficient in front of oxygen. So I'm trying to get moles of oxygen. And this 2 is just from the coefficient in front of H2O2, way over there. Okay. So this is just going to be 4 divided by 68. All right, so 4 divided by 68, 4 divided by 68. So a pretty small number of moles. I got 0.059 moles of oxygen. So now I have my moles of oxygen. All right, I'm not done yet. I still have to figure out the pressure using the ideal gas law. Any questions so far, though? So I don't know if you guys have any questions. This is probably the hardest kind of question you could probably get on the test, but again, I would chunk it into different parts like this for you guys. Or it would be clearer than this because I'm on like a really small whiteboard and I couldn't even write the full description up here of the question, so I apologize about that. But it'd be clearer on the test. And there'll be one like this on the study guide that we can practice too. Also, next week, I'll post the odd numbered solutions to the homework problems, and I'll post most of the study guide solutions as well. Like not just the odd ones, but most of them, not every single question, but almost all the questions. So anyways, we have that many moles of oxygen. I'm looking for the pressure here, so let's get pressure by itself. So pressure is going to be nRT over V the moles we just found, that was 0.059. The R, we're looking for the pressure in atmosphere, so it has to be 0.0821. And the temperature is 500 Kelvin. And the volume is 250 milliliters. Excuse me, guys. The volume going down here is 250 milliliters, but I need it in liters. I need this in liters for the R constant because I couldn't fit all the units here, but the unit for R is liters. So just move the decimal 3 spaces to the left, right? So it's actually 0.25 liters, so a quarter of a liter. So it would look like that. Right, so first we were down here, we went from grams of hydrogen peroxide to moles of oxygen. That's what we did first, right? Just using the mole house. So we divided by the mole mass of H2O2, use the coefficients from the equation here to get moles of oxygen. This is H2O2, that's oxygen. I just didn't want to make it too crowded. So we got the moles of oxygen, and that's I plugged up there. That's at that 0.20, is that 29? Yeah, 0.59. It looks like a mirror for me. 0.59 is up there. Let me make sure it's in there correctly. 0.059. Sorry, guys. It's weird reading this backwards. 0.059 is up there. That's the moles I just found. And it wanted the pressure in atmosphere. So I'm using 0.0821 because that's the R constant for a pressure in atmospheres. Right? That's just from the notes, just a constant. And T is the temperature. That thing right there. And the volume is 250 milliliters, but I have to have it in liters. So you move the decimal 3 spaces to the left, so you get 0.25 liters. So let's see what we get here. Let me just double check. Just make it quicker for you guys. Times 500, 9.65. Yeah, so it's pretty high pressure. You get 9.65 atmospheres. So flimsy. This whiteboard is like a flimsy piece of paper. It's so uncomfortable. Anyways, so there's the pressure, 9.65 atmospheres. So this would be like the hardest question you'd see on the test. You would just have to do one part where you do a stoichiometry problem. Be quick like this, right? Be kind of quick just to go to moles of the other substance. And then that's what you're going to plug into the equation up here. Right. Any other questions about this one, though? I'll do a Dalton's Law example as well, but let me know if you guys have any questions about this one. All right, so the first step is really down here on the bottom, and the second step is using the ideal gas law. And again, on like the study guide or the test, I'd make it very, what's the word? Very like step by step. So first, you would just focus on figuring out how many moles of oxygen you have. And I'd even probably tell you guys, hey, it's a stoichiometry problem. The second part would be using the ideal gas law. Yeah, I can look at a Dalton's Law example. Here, 1 second, let me see if I can get. I just had to double check something. All right, so Dalton's Law. Let's see. Try to find a good example for you guys. Dalton's Law is probably, I guess you'd say, the most straightforward one. So I'll just show you guys this one. So it's just a sum. So again, Dalton's Law is just the total pressure of gases in a mixture is just those individual pressures all added up. Right? So it's pretty much like this. It doesn't have to be 3. It just has to be at least 2. As many gases as there are, that's why there's ellipses right here. Right? My vocab's not too good. I forgot what that word means, to be honest. So, all right. So we have 3 different gases in here. So yeah, we have oxygen at 2 atmospheres. Now let's find a different example. That one's almost like too straightforward. Um, so again, the wording is going to be kind of short, just because I'm trying to save space on here. So for something like this, right, it's really just a sum. So this is a probably the, I guess, most simple of the gas laws, really. Dalton's law is just a summation. So the total pressure is equal to the sum of all the individual pressures, right? So we have oxygen at 5, CO2 at 3, and helium at 4, right? So it's just going to be 2, not 5. I'm looking at this backwards. 2 plus 3 plus 4. So you get 9 atmospheres total. So yeah, it's just going to be like a summation, just adding them together. You might sometimes get a case where, you have the total pressure and you have like two of these, but you're looking for the other ones. You just have to subtract on both sides. That's pretty much it. The most complicated this could get is if you have a different unit for pressure. Maybe it said this is an atmospheres, that's an atmospheres, but maybe this was kilopascals or something. Then you just need to convert that to atmospheres. It doesn't really matter what unit you convert it to, as long as they're all the same gas unit. So it's really just like a summation, but you just have to make sure they're all the same unit. This one was pretty quick and simple because they were all in atmospheres. But it would be more complicated if they were like each a different unit, like atmospheres, millimeters mercury, kilopascals. Then there's pretty much multiple correct answers. It just depends on which unit you want to choose to use. You just have to convert them into that one unit, though. Yeah, let me know if you have any other questions, though, guys. If you want to look at any other examples at all. Yeah, the gas stoichiometry problem is probably the one that would be the longest that we'd look at, or the most difficult one we'd look at. Yeah, so tomorrow's quiz is just Charles' law, Guy-Lussac's law, Boyle's law, and the ideal gas law. Just 4 questions, one of each. Pretty quick and simple. And then next week we'll just have the study guide to be working on pretty much. So it'll be pretty short and sweet for next week as well. Oh, the c is the speed of light. That's a constant. So it's just talking about matter and special relativity. Um, Basically, when matter is like going close to that speed of light, it's easily convertible. It's pretty much the same thing as energy. So matter and energy are really kind of like one. Even if you think about like what we're made of, for example, atoms, we're mostly empty space. We have this solid appearance because of the energy that each of these atoms is basically holding and vibrating at. So yeah, basically, when it comes to the speed of light, or it's also like the same thing as just like pure energy, pretty much. Like it's going the fastest speed possible. So yeah, c is the speed of light. There's a longer version of that equation too. It's actually more accurate. Um, where is it? Where it also takes into account time. I can't find it. Yeah, it uses the Lorentz factor. That's right. I can't find the one I was thinking of. But yeah, c is basically just the speed of light. Yeah, when you're going that fast, basically it bends space and time in such a manner that time like moves a little bit slower, pretty much, if you're going that quickly. It's a strange thing because time is not just one thing itself; it's involved with space. They're kind of interwoven with each other. So yeah, it gets pretty interesting. I'm trying to see if there's a good example. Like, uh, see if I can find a good one. Because usually, like even when I was teaching AP Chem or AP Physics last year, we didn't get into special relativity much. Just we barely started looking at it, but we didn't spend a lot of time on this equation. It was towards the end of the year. Um, so yeah, it's interesting because an equation like that unites both conservation of energy and conservation of mass. Because mass can neither be created nor destroyed, same as energy, but they can be converted into each other. So even if it seems like mass is gone, if you don't get the same amount of kilograms before and after, which is what happens in some reactions, like fusion reactions and fission reactions. When it comes to that higher field of physics, it might seem like the mass is gone, but it was converted into energy, or was released as energy. So it's interesting. Yeah, I'll take it easy, Mohammed. Yeah, let me know if you guys have any other questions or anything. I might take off in a couple minutes though. Just make sure I have the study guide for next week ready. Mm. So yeah, things like fission reactions, like really heavy elements that decay and send out like gamma rays and stuff like that. You use that equation to figure out how much joules of energy they're emitting as they decay. So when it's moving at a certain like a very fast enough speed, yeah, it's pretty much the same as getting converted into energy. Or if it's decaying, for example, there's different examples, different like scenarios, I guess you could say. So if it's let me see if I can find a good one. Do, 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 do. So yeah, because when mass gets converted into energy, it moves at that speed, at close to the speed of light. So that's why it's used in that equation. Like, trying to see, like this one. I don't know if I can copy it over there. So kind of like earlier last semester when we looked at those. So here's one part of the question, kind of like earlier last semester when we looked at nuclear decay equations, like alpha decay, beta decay, gamma decay. It's this kind of stuff pretty much. So if you have thorium on the left side and then you have the arrow there, like let me see if I can type it out. Thorium goes to radon, right? And we're trying to figure out the energy that it's emitting, right? So that's why it's blank there. So we know that 2 grams is missing, right? We had 2 kilograms. Sorry, 2 kilograms is missing. We had 10 kilograms of thorium. Now suddenly we only have 8 kilograms of this radon plus this energy it's emitting as most likely gamma rays. So we're trying to figure out how much energy that's really emitting. And so that's when you use the MC squared equation. So it'd be something like this. 2 kilograms times the speed of light, which is 3 times 10 to the power of 8. No, not the star, the number 8. So yeah, something like that. Oh, that should be squared though. that should be squared. 3 times 10 to the power of 8 all squared. Yeah, it'd look more like that. It has to be squared. So yeah, the speed of light is just 3 times 10 to the power of 8 meters per second. So it's just a constant. Yeah, those questions aren't really that common in high school. Maybe like because even in AP Physics last year, we saw some of those questions kind of like at the end of the year for just a little bit. Yeah, I'm probably gonna take off that now though. It looks like my computer's about to die. Yeah, I hope you guys have a nice, safe rest of your day, and take it easy. Let me know if you guys have any questions or anything like that. I'll see you guys later. Take it easy.